Since the first artificial neuron in 1943, AI development has prioritized computation and generation, transitioning from tools following static instructions to systems that interpret goals. By 2025, the industry focus shifts to agentic AI, autonomous systems designed to independently plan and execute complex tasks. An agentic system looks like this: a mechanical bike balancing itself upright, calculating microcorrections and executing them through a motor, functioning without a human rider. Building these systems require reinforcement learning. However, the standard training algorithms are notoriously unstable. A system can learn a successful behavior in 1 hour and destroy that progress through a single aggressive update in the next. This instability creates a massive legal hurdle. As agents take physical control over hardware, they trigger the strict compliance obligations of the incoming European Union AI Act. Deploying a modern autonomous agent requires dual mastery. Developers must satisfy the strict legal classification criteria of EU compliance while maintaining the mathematical training stability of Proximal Policy Optimization. Under Article 6 of the EU AI Act, a system's intended purpose determines its regulatory burden. If an AI is designed for a high-risk application, it is subject to mandatory risk management and data governance. For autonomous control, these requirements trigger if classified as a safety component. It qualifies if it performs a direct protective function, preventing risks to health, safety, or property, or if its failure creates a safety hazard, regardless of its primary goal. This creates a trap for general-purpose AI. Systems with broad capabilities are considered high risk unless providers explicitly exclude these uses from their technical documentation. Any agent built for physical or digital control is practically guaranteed to meet these criteria. To legally deploy such a system, developers must document and prove the agent's technical reliability. Proving that reliability requires a move from legal definitions into the internal architecture of the control agent. In our bike simulation, the agent receives a constant stream of data, the environment state, and must output continuous control actions to maintain equilibrium. The processor is an actor-critic architecture, splitting the environment state into two neural network blocks. The actor network learns the policy, mapping state variables directly into physical balancing actions. The critic network provides a baseline, estimating each state's value to judge performance and reduce variance. If you train this architecture using a vanilla policy gradient, you encounter a destructive update problem. When the actor network discovers a successful action, it can update its policy too aggressively. It over-indexes on a single positive result, which wipes out the previously learned behavior. In the simulation, this looks like a sudden, violent twitch. The bike overcorrects, loses its structural stability, and collapses. These unconstrained updates make the system unpredictable. Because a safety component must be reliable by law, a vanilla policy gradient is often technically insufficient for deployment. To solve this, developers use Proximal Policy Optimization, or PPO, which adds a mathematical constraint to the training loop. This is the PPO-clipped objective equation. It enforces stability by deconstructing how the policy changes over time. The variable r sub t of theta represents the probability ratio. It compares how likely an action was under the old policy versus the newly updated one. If left unbounded, the policy drifts significantly in a single step, causing a performance collapse. PPO prevents this by establishing a clipping range. It clips the ratio if it exceeds a hyperparameter. This clipped ratio is then multiplied by the critic's advantage estimate. The equation creates a soft penalty for large changes. It allows for improvement, but restricts the aggressive leaps in logic that destabilize an autonomous agent. By enforcing this mathematical boundary, PPO provides the consistent learning curve necessary for an agent to function safely in a physical environment. While legal compliance requires human oversight and strict documentation, those mandates are impossible to meet without a stable model. PPO provides the technical foundation for the high-risk reliability standards demanded by regulators. However, this stability is not automatic. Reinforcement learning is highly sensitive to the clipping range and the learning rate chosen during training. During development, poor results are often a symptom of an incorrect configuration in these parameters, rather than a failure of the PPO algorithm itself. Agentic AI moves beyond the text generation capabilities of large language models. It requires specialized control systems that can survive both the mathematical variance of training and the strict regulatory scrutiny of the real world.